All right, hello everyone. Thank you for joining me again, and let's continue on our quest. So, as mentioned in the previous video, we have two objectives. Now, the one objective is to understand different IPv6 unicast addresses, and the second one is we want to get these two PCs, which I've changed one of the PCs to a web server, to be able to communicate with each other. Now, to accomplish this, we need to role play a little bit. All right, we need to role play. And since one of our objectives is to understand IPv6 unicast addressing, we need to present or develop a scenario that would allow us to fully comprehend unique local addressing. Now, to do this, I modified the scenario a bit, and I'll explain. Now, we know that unique local addresses are synonymous with IPv4 private addressing, right? Well, if that's the case, private addressing cannot be announced or routed out to the internet. So this link between Acme Edge and ABC Edge, this link here, has to be a private dedicated link. It could also be an IPsec GRE tunnel, to which you can actually create neighborships between two different geographical locations, depending on the use case that you're presented with. But for all intents and purposes, we have to assume that this is a private, dedicated link between two locations. So now that we have described the scenario, we need to talk a little bit about an autonomous system. Because as you can see, I've created this square box to illustrate an autonomous system. So you're probably saying, well, what is it? And it's probably one of the most important concepts we need to learn in networking. And here's my definition. An autonomous system is a collection of network devices that are strategically configured to participate in a routing ideology. Okay? All the network nodes share a common collective consensus on how traffic will flow through its network. An autonomous system is a collection of network devices that, while they may seem separate, they act as one unified body. Okay? Now, you must be wondering, well, how do you create an autonomous system? Well, the answer is we create an autonomous system by choosing an internal gateway protocol, whether it be OSPF, RIP, EIGRP, that will ultimately allow the network devices to understand, learn, and comprehend traffic patterns on their own autonomously. In the end, we're working to create a system made of routers, switches, firewalls that basically work together to be autonomous. Now, the trick is to study every single IGP that exists and comprehend its intrinsicies, characteristics, and attributes of each internal gateway protocol, and understand its place in your autonomous system design. There is a certain sense of craftsmanship when designing an autonomous system. So, moving forward, I decided to make some of the changes with regards to what we just spoke about. So number one, I'd like to just take a look at my configuration here. So number one, I inserted the orange box to cover what our autonomous system is. Now this design is very basic and is used to help us through the journey of understanding. Okay? Secondly, I guess we can take a look at the config now. If we look at my configuration, I took the auto configuration command off the interface. Okay? Because I wanted to see how the routers would behave otherwise. Thirdly, the interconnection between Acme Edge and ABC Edge, as shown here, has not been configured, but we will be covering that very soon. And most importantly, I did some IPv6 subnetting. I took the unique local address, as you can see here, and I carved it out to a /61. This will allow us to have 7 subnets from 0 to 7, but we'll only be using 6. So for example, the 0 subnet is for the core. The one subnet is for the relationship between the PC and the router. And subnet 2 is for the interconnection to ABC edge 2. Now on ABC's side, okay, we have the core that is subnet 3, and then we have the relationship between the router and the web server in subnet 4. Now, I just want to bring this up, and this is a fantastic tool because it allows you to be able to identify how many subnets you can have based on this prefix that you've defined. So as you can see, 61 gives us from 0 to 7 and these many hosts. So why don't I just go and apply this configuration, and I'll be right back. All right, perfect. I've applied the configuration, and now I want to show you a couple of things. Let's first take a look at the config. As I mentioned before, I took off the IPv6 address auto configuration command, and I statically configured a unique local IPv6 address, unicast address on the interfaces. And I've also assigned them to the correct subnet, and I've assigned them the host value that I wanted them to have. So how does this look on the actual router? So if I go onto the routers and I do a show IPv6 interface brief, something interesting actually really happens. So once I statically configured the unique local address on the interface, it also assigned automatically a link local address in companionship. And the reason is very simple. The link local address space will always be present to share neighborship information with other participants on the shared link. And this rule is true for all the others as well. Okay? Now, another thing that I did that I thought was pretty cool is I said to myself, geez, IP version 4 addresses are a lot easier to look at. They're much better to look at than the 128-bit hexadecimal value. So knowing that the preceding zeros of the IPv6 address space get removed once I press enter, I decided to use that to my advantage. So when deciding what address space I wanted to actually have in here, in this particular area of the depiction, I logically chose the IP version 4 address space 10.100.100.0, to which, when I applied the actual configuration on the interface, you can see that my 10.100.100.0 is actually visible in the IPv6 addressing scheme. You see it here, and you also see it here. And the same rule applies for ABC company as well. Now, the reason why that's important is because if you look, it's a lot easier to view the IPv6 addressing structure at this point. I know that this interface is in subnet 2, and it has the IP address of 10.1.1.1. Even though it's interpreted as an IPv6 address, it's visually much easier to recognize when it's depicted like that. Now, the other thing I wanted to show you was this. Now, we know that unique local addresses are routable, okay? So does that mean that the IPv6 addresses are now finally being populated into the routing table? Well, let's take a look. If I do a show IPv6 route, I can finally see IPv6 eligible routes being populated into the routing table. So the next question is, does that mean that PC1 can finally ping Acme Edge's Gigabit Ethernet 01 interface? Well, let's give it a shot. What I'm going to do is I'm going to take Acme Edge's 01 interface, which is this. I'm going to go on PC1, and I'm going to try and launch a ping. Okay, now as you can see, we're getting timeouts. But how can that be when the IPv6 unique local addresses are actually being populated into the IPv6 routing table? Well, it's kind of easy of an answer. If I was to turn on Wireshark, and Wireshark is monitoring this particular link right here. Okay, it's monitoring this link right here. if I was to launch that ping again, you can see the packets are actually arriving to Acme Edge's Gigabit Ethernet 01, but not returning back. Why? Because we don't have routing. We have correctly configured the physical interfaces, and everyone in this routing domain is predisposed and willing to participate. However, we haven't applied an interior gateway routing protocol. And until we do, Acme Edge will never be able to understand how to return back to that IACMP request. Make sense? So what I'm proposing that we do is take a look at this configuration that I've come up with, and I'd like to propose OSPF version 3. So OSPF version 3 is solely for IPv6 purposes, okay? It is meant and developed to route IPv6 prefixes. Now, there's one little quirk with OSPF version 3, and that is that it relies on a IP version 4 IP address to use as its router ID. So having said that, I configured router loopback 1 or interface loopback 1. I've assigned it its loopback address, and I've configured OSPF as follows. It's a very basic configuration, and we haven't even scratched the surface of the complexity of this routing protocol, but for all intents and purposes, it will help us move forward in this particular diagram. Now, what I also want to do is just keep an eye on this particular command right here. What this command does and what it means is that it's going to automatically instantiate the default route into its OSPF updates, meaning that everyone in this routing domain or participating in this OSPF instance are going to learn about the default route via Acme Edge. As you can see, Acme Core, which is a router over here basically on its own, he has a very similar configuration, but even more basic. And if you take a look at Acme 2, it's very much the same thing, with one little quirk. With this particular router, because he's connected to PC1, I've opted to redistribute the connected subnet into OSPF. This should allow Acme Edge to be able to reach it. And again, I'm taking this particular subnet and I'm telling this router to say, take this subnet, take this particular IPv6 address and dump it, place it, redistribute it into the OSPF domain so then Acme Edge can actually recognize it and be able to route back to it. So let me apply the configuration and I'll be right back. Perfect. So I just applied the configuration. So let's check to see if PC1 can reach Gigabit Ethernet 01 on Acme's Edge inside interface. Now, before I do that, I have something that I'd like to mention. In the previous video, I mentioned that OSPF is used to solely route IPv6 packets, knowing very well that OSPF version 2 only supports IP version 4. However, when I began reviewing the configuration and began applying the configuration on the router, I noticed that OSPF does have the address family IPv4 eligibility, as you can see here. Now, this was strange to me, so I followed up by reading the RFC. And in fact, it looks like OSPF may support IP version 4. This is the RFC. Now, I've never personally used it though. I haven't tested it either. But I also thought it would be appropriate to disclaim that IP version 3 does support IP version 4 in some capacity. Now, moving forward, let's do some testing. So I'm going to go on to PC1. Actually, let me just grab the inside interface of Gigabit Ethernet 01. I'm going to go to PC1. And I have successful pings. Why? Because I've just applied routing. And Acme Core 2 is now announcing to everyone in this routing domain that he knows how to get to FD00 10.100.100.1 and also knows how to get to FD00 1, the PC's MAC address. Perfect. Now, I'd like to mention that everything that we've done here, I've replicated here. The only thing that's missing now is this portion. So why don't we go ahead and turn on this interface and see if we have end-to-end reachability. So to do that, I'm going to go to Acme Edge and take my configuration, config T, area 0 looks good, Edge, and now we got to go to the next one. Let's wait for the adjacency to come up, and then we'll begin testing. So this is an IP, and we're going to ping from PC1. I'm just going to get it ready. But let's take a look at Acme Edge. I think it takes a couple of seconds for it to come up, but it should come up. All right, there you go. The adjacency is up. So here we go. Let's give it some time. And there you go. It looks like it just needed some time, and now we have reachability. We have successfully completed our mandate. We now have PC1 reaching this web server in a fully 110% IPv6 based prefix scheme.